Here's another example of a reaction. We don't need to know the details of the reaction, but another example where a reaction has the potential for generating stereoisomeric products. So as the semester goes on, we're going to be very concerned with this. We're very interested in this, let's say. Reactions where more than one stereoisomer is possible, and then seeing if there are certain reaction conditions wherein one of the stereoisomers is favored. So stereoselective reactions will be near and dear to our heart. So in the last couple examples, our starting compound has been a carbonyl, and we've added nucleophile hydride to that carbonyl. In this case, let's start not with a carbonyl compound, but with an alkene. Okay? So this particular alkene is related to butane because it has 1, 2, 3, 4 carbons. So let me just number those carbons here. 1, 2, 3, and 4. So this would be named as a derivative of butane, except it's not an ane, it's an ene because it has a double bond in it. So it would be butene. And then, you know, if you have a 4-carbon chain, the double bond could be in the middle or it could be at the beginning. So we have to specify where the double bond is. So the double bond starts at carbon 2. And then, what do you know about a carbon-carbon double bond? So, you know, when you have a carbon-carbon single bond, you can just rotate very easily around the carbon-carbon single bond. Do you know in a carbon-carbon double bond compound if you can do that? No, you can't, because that would force you to completely break the pi bond, and that costs too much energy. So there's no rotation around a carbon-carbon double bond. Okay? So there are actually 2 stereoisomers of 2-butene. One that looks like this, right? And then the other one would look like this, in which the 2 methyl groups are in this relationship rather than being on the same side of the double bond. Okay? So just to point this out, because there is no rotation around this carbon-carbon double bond, this molecule cannot readily convert into this one, or vice versa. So notice these two are, they're not structural isomers because all of the atomic connectivities are the same. So they're stereoisomers. So first question for you, do you remember the 2 different types of stereoisomers? So the 2 broad categories of stereoisomers. You have enantiomers. These are non-superimposable mirror images. And then you have everything else. And the everything else category, those are called diastereomers. So what type of stereoisomer do you think we have here? If this butene wakes up in the morning and looks in the mirror, does it see that? No, it does not. Okay? So these are not enantiomers. They are diastereomers. Okay, so that's just a little preview of when we start talking about the chemistry of alkenes. So in terms of naming, we'll have to have a name for these. Because these 2 methyl groups are kind of on the same side of the double bond, this is known as cis-2-butene. And because these 2 methyl groups are apart from each other on the carbon-carbon double bond, this is known as trans-2-butene. They're both 2-butene, but they are diastereomeric forms of 2-butene, so we have to be able to distinguish them in terms of the names. Okay? All right, well, that's kind of a little bit of a digression. I want to focus just on this one, on cis-2-butene. And I want to just invent what for now is going to be kind of a magical process, but later on in the semester we'll talk about how this chemistry might actually be done. It can actually be done with real reagents and in the lab and everything. But let's just imagine a magic reaction called dihydroxylation. And as the name implies, you're going to add 2 hydroxyl groups to cis-2-butene. Okay? What is a hydroxyl group? A hydroxyl group is an HO group attached to something. So here's a hydroxyl. So here's what we're going to do, okay? We are going to add an OH group to carbon 2, so one of the carbons of the double bond. And we are going to add an OH group to carbon 3. And what I want you to think about is how many stereoisomeric products might result from that dihydroxylation process. Now, if I'm going to add an OH group to carbon 2 and I'm going to add an OH group to carbon 3, the double bond can't be there anymore in the product, right? So this magical process also consumes the double bond. So I just tried to attach more things to carbons 2 and 3. I would exceed the octet at those carbons, okay? So you're going to add OH to carbon 2, you're going to add OH to carbon 3, and the double bond is going to be gone, and we're going to call this process dihydroxylation. And I want you to think about the possible stereoisomers, and in doing so, I want to try to connect this to the previous problems that we did. What's the hybridization and what is the geometry at carbon 2? Well, this is sp2, trigonal planar. And how about at carbon 3? That's also sp2, trigonal planar. So what can I say, and maybe this is a hint, okay? What can I say about the geometry of this carbon, this carbon, this hydrogen, this hydrogen, this carbon, and this carbon, given the hybridization of carbons 2 and 3? How do they lie with respect to each other? And the picture is trying to do that justice. The whole carbon-carbon double bond unit and the 4 things that are attached to it lie in one plane. So just like in the carbonyl example, we start with a flatness associated with the carbons where we're going to add new groups. Okay? So does that help? And then my advice is keep this chain oriented in exactly the same way. So the OH groups could come from the front. Maybe both of them would come from the front. Both of them could come from the back. You get the idea? One could come from one could come from the other, etc. Okay, so what are the stereochemical possibilities? That's what I want you to think about. What are the stereochemical possibilities in this kind of hypothetical dihydroxylation reaction? So pause the video and see if you can work through that. We're using cis-2-butene as our starting material. Well, let's just take this systematically, right? I can imagine 2 different pathways. In one pathway, both OH groups would be added from the same face of the alkene. So in other words, both OH groups could come from the front of the board, or both OH groups could come from the back of the board. So let's start with those 2 possibilities. Draw what you would get if both OH groups come from the front. Draw what you would get if both OH groups come from the back. So here, I'm just going to keep the backbone of the molecule constant, just to keep myself oriented. And then if the OH groups came from the front of the board, there would be one of them. And then this is a dihydroxylation. So here would be the second one. And what is the consequence of that? Well, the hydrogen then has to be back. And the hydrogen here has to be back. So that would be both OHs coming from the front, okay, or the top. In chemistry, the top face, sort of for historical reasons, is sometimes called the beta face. Top equals beta, more or less. And the bottom face is often referred to as the alpha face. So I'm just going to label this as alpha OH, beta OH, and a second beta OH. Okay? What if both hydroxyl groups had been delivered from the back of the board? What would the product be? Well, the OH group would be back here, and this OH group would be back. And the consequence for this hydrogen is that this hydrogen would be forward, and this hydrogen would be forward. So we might call this the alpha compound. Okay? So maybe you got those two. So that's the scenario where both OH groups are added from the same face. But we really don't know anything about this kind of mythical, for now, dihydroxylation reaction. What if the details were that one OH came from one side and the other OH ended up coming from the other side? I mean, that might be possible. So what are the options in terms of that mode of dihydroxylation? Can you draw those products over here? Well, I think I just need to, hang on, make a little bit more space here. Let me just erase the name of trans-2-butene here. And let me just divide this up here. So again, I'm just going to keep the backbone fixed. There we go. And I'm going to do the same over here. So those are the 4 carbons of trans-2-butene. And now I want to draw the products where one OH came from one face and one OH came from the other face. So one possibility would be for the first OH to come from the top. So there we go. There. That would be a beta OH. And then at the other carbon, the OH would come from the back. So that would be an alpha OH, and the hydrogen would be here. And then there's one other possibility, which would be the other way around. If at this carbon the OH had come from the back, I would have something that looks like this. So here's an alpha OH. And then over here I would have a beta OH and the hydrogen back. Okay, so these are the 4, well, maybe apparently 4 different ways of doing this. I just want to, I want to introduce you to a little bit of terminology here. When you do 2 things on the same face of an alkene or some other group of this type, on the same face, that is called a Syn addition. Okay, so these would be examples of Syn addition. So that just means same face addition. This mode of addition, where one group adds from one face and the other group adds from the other face, this is known as anti-addition. Okay? So now what I want you to do is to look at these 4 structures as drawn and see if you can outline the stereochemical relationships among these different structures. Okay? So you have 4 pictures, 1, 2, 3, 4 pictures. And what I need to know is a pairwise dissection of, you know, is this the enantiomer of that or the diastereomer of that, or what are the relationships? So pause the video and take a look at that. Okay, well, let's start with this compound and this compound. So remember, in this compound, the two OH groups added to the top face of the cis-2-butene is drawn over there. In this case, they added from the back face. And what is the relationship of these two compounds? Well, you may notice that they're the same. All right? So cis-2-butene is a symmetrical molecule. And so if you do a Syn addition of two identical groups, OH and OH, you end up with a compound that has a plane of symmetry right here. And so if you take this and you turn it over, you get identically the other one. Okay? Is this molecule chiral? No, it is not. Okay? If you can find a plane of symmetry, it can't be chiral. So this molecule, and if there's just one molecule here, right, just turned over, this is an achiral molecule. How about the relationship between this compound and this compound right here? What is the relationship there? Well, the way that they're drawn, you see this is a mirror image type of relationship. So if we look at this as a mirror plane, this OH reflects into that, this reflects into that, and so forth. So they are mirror images of each other. Are they the same? So if I took this and I scooted it over here, would they match up? No, they wouldn't, because this OH would go there. Well, could I take this picture and turn it over and make it match? That doesn't work either, because when I turn this over, this hydrogen ends up where this OH is. This OH ends up where that hydrogen is. So these are non-superimposable mirror images. What's their relationship? These are enants. And then there's one more relationship, or I guess two more relationships to be determined. Remember, this is just a single compound here. So what's the relationship between this stereoisomer and this one? And what's the relationship between this stereoisomer and that one? That finishes out the different relationships, stereochemically speaking. Well, these are stereoisomers that are not enantiomers. So they are diastereomers. And over here, this is also a diastereomer of that. Okay? So just to review a little bit of terminology, and I think this came up in the class that you had with Mahendran. Here we have, this is just one compound, remember. We have an achiral member of a set of diastereomers that also contains chiral molecules. So this molecule is chiral, right? It has an enantiomer. And so is this one. So we have a set of 3 stereoisomers, 2 of which are in fact chiral. But there's the third one, which is achiral. This type of situation, this type of compound, is referred to as a meso compound. All right? M-E-S-O, not like the soup. And so this compound right here, and there's just one compound, is called a meso compound because it is an achiral set of a larger set of stereoisomers, which also includes some chiral members. A tip-off that you may be dealing with a meso compound is if you can find a plane or a center of symmetry in the molecule, and even though you have, in this case, 2 carbons with 4 different things attached, the molecule as a whole is achiral. So again, just to point out, there are many times, and we will see many examples of these reactions this semester, where you start out with a carbon that is, say, sp2 hybridized, which is not one of these tetrahedral centers with 4 different things attached, But then there's some chemistry that occurs, and we haven't said exactly how one would do this, but we will later in the term. There's some chemistry that takes place and now generates, in this case, 2 new carbons of the type 4 different things attached, and then we have to think carefully about the stereochemical possibilities, right? Ideally, we would have some chemical methods to selectively make this one. Say we wanted the Meso product, selectively make that one. Or say we wanted the chiral product, selectively make this. And we won't talk about this so much, if at all, in this class this semester, but there is technology available to humanity in our current day that would allow you to favor not just the chiral molecule versus the achiral one, but actually one or the other of the 2 enantiomers of the chiral material. So that's an area known as asymmetric synthesis. It's very important in organic synthesis, and we may be able to see some examples of that this semester, but it's really, as they say, a little bit beyond the scope of what we will be covering in the introductory organic chemistry course. Okay? So again, we have pro-chirality at the double bond carbons because those sp2 centers, if they're converted into sp3 centers under these types of conditions, you could end up with stereoisomeric products. Okay. That's it.